Tonight, we're going to talk about 5 objects, not 5 planets, not 5 stars, not 5 galaxies billions of light years away. 5 objects that human hands built, human minds designed, and human rockets launched into the sky from a small blue planet in an unremarkable corner of the Milky Way. 5 objects that are, right now, tonight, as you're listening to this, moving through a darkness so complete and so vast that the words we normally reach for when we try to describe space simply stop working. They become insufficient. They point at something without capturing it. 5 objects that have done something no other human-made thing has ever done. They left, not just left Earth, not just left the inner solar system, not just past Mars or the asteroid belt or Jupiter or even Saturn or Uranus or Neptune. They left the solar system entirely. They crossed the boundary where the sun's influence ends and the true interstellar void begins. They are, right now, traveling through the space between stars, the same space that separates us from every other sun in the galaxy, the same emptiness that makes the distance to the nearest star feel, even to minds that have spent years thinking about it, like something that cannot be real. And they are still going. By the time you fall asleep tonight, each of those 5 objects will have moved further from Earth than they were when you started listening. Not by inches or miles, by tens of thousands of miles. Moving outward, always outward, into a darkness that has no center and no edge and no map. I want to tell you their stories, not as engineering achievements, though they are extraordinary ones, not as political triumphs, though there was real political will involved in making them happen, but as what they actually are. 5 messengers, 5 bottles thrown into the deepest ocean imaginable, each one carrying something of us, each one finding something that had never been found before, each one now alone in the dark between stars, still moving, still transmitting, or long since silent, carrying human fingerprints into a void that existed for billions of years before any hand existed to make a fingerprint. This is a quiet story, slow in some ways, fast in others. It involves some of the loneliest numbers in all of science. And by the time we're done, you're going to understand what it actually means. That we did this. Not just the physics of it, the human weight of it. Before we get started, if you love exploring the depths of space and the great unanswered questions of the cosmos as much as we do here, take a moment to like this video or subscribe to the channel. It helps more curious minds find their way here, and it keeps this journey going. Now, let's begin. Let's start with something that sounds simple, but isn't. What does it actually mean to leave the solar system? Most people, if they draw the solar system in their heads, picture it ending somewhere around Neptune, or maybe a little past Pluto, the last planet, or the most famous dwarf planet, and then the boundary. Beyond Neptune, the thinking goes, is somewhere else. Interstellar space. The void. But that picture is wrong. Not slightly wrong. Fundamentally wrong in a way that, when you understand it, changes the scale of everything. The solar system doesn't end where the planets end. The planets end relatively close in. Neptune, the outermost major planet, orbits the Sun at an average distance of about 30 astronomical units. 1 astronomical unit, or AU, is the distance from Earth to the Sun, roughly 93 million miles. So Neptune is about 2.8 billion miles from the Sun, which sounds enormous until you understand what comes after it. Beyond Neptune lies the Kuiper Belt, a region of icy bodies and dwarf planets. including Pluto, extending from about 30 to 50 ATUs from the Sun. Beyond the Kuiper Belt, there's a more distant and thinly populated region called the scattered disk. And beyond even that, astronomers believe, lies the Oort cloud, a vast spherical shell of icy bodies that may extend from 2000 AU all the way out to 100,000 AU from the Sun. That outer boundary is nearly 2 light-years away. The Oort cloud, if it exists as theorized, is so vast that the nearest star, Alpha Centauri, is only a few times farther than its outer edge. Our 5 spacecraft are nowhere near the Oort cloud, not even close. So when scientists say they've left the solar system, they're not talking about leaving the gravitational sphere of the Sun's influence, which extends almost incomprehensibly far. They're talking about something more physically definable and in some ways more meaningful. They're talking about the heliosphere. The Sun doesn't just radiate light. It radiates matter. Constantly, in every direction, the Sun expels a stream of charged particles, protons and electrons moving outward at hundreds of miles per second. This stream is called the solar wind. It flows in all directions simultaneously, pushing outward against the interstellar medium, the thin gas and dust that fills the space between stars. For a certain distance around the Sun, the solar wind is strong enough to dominate the local environment. It pushes back against the interstellar medium, creating a vast bubble of solar influence. That bubble is the heliosphere. Everything inside it is, in a real physical sense, in the Sun's territory, bathed in solar particles shaped by solar magnetic fields, connected to our star by a continuous stream of material that flows from its surface. The heliosphere is not perfectly spherical. The Sun moves through the galaxy, and as it does, the interstellar medium presses harder on the leading edge. But it's roughly spherical, and it extends to about 100 to 150 ATU in most directions. That's 3 to 5 times the distance of Neptune. At the edge of the heliosphere, the solar wind slams into the interstellar medium and slows abruptly. This boundary is called the termination shock. It's a real physical transition, not just a conceptual one. Crossing it involves measurable changes in particle speed, particle density, magnetic field orientation. The region between the termination shock and the outer edge of the heliosphere is called the heliosheath, a turbulent mixing zone where solar wind and interstellar medium interact in complex ways. The outer boundary of the heliosphere, the actual surface of the Sun's bubble, where solar influence ends and interstellar space begins, is called the heliopause. When scientists say a spacecraft has left the solar system, they mean it has crossed the heliopause. It has left the bubble. It is, for the first time, in space that is no longer shaped by our star, space that belongs to the galaxy rather than to the Sun. 2 of our 5 spacecraft have done this. One of them, definitively. The other perhaps, though the evidence is less clear. The others are still inside the heliosphere, still within the Sun's bubble, hurtling outward toward a boundary they will eventually cross. And all 5 are still moving tonight. Let me introduce them now. All 5. Their names, their launch dates, their basic trajectories, and where they are as you listen. Pioneer 10, launched March 2nd, 1972. The first spacecraft to travel through the asteroid belt. The first to make direct observations of Jupiter. The first human-made object to travel beyond the orbit of all the planets. And the first to travel in the direction of interstellar space. Pioneer 10 is currently heading in the general direction of the star Aldebaran, in the constellation Taurus. At its current speed, it would arrive in the vicinity of Aldebaran in roughly 2 million years. Though Aldebaran isn't its destination, just the direction it happens to be heading. Its last signal to Earth was received in January 2003. It has been silent since. But it is still out there, still moving, now approximately 135 AU from the Sun. Pioneer 11, launched April 6, 1973. It followed Pioneer 10 to Jupiter, then used Jupiter's gravity to slingshot towards Saturn, becoming the first spacecraft to visit Saturn directly. It discovered new rings and 2 new moons of Saturn. Its last signal arrived in November 1995. It is heading in a direction roughly opposite to Pioneer 10, toward the center of the galaxy, in the constellation Aquila. It is now approximately 105 ATU from the Sun. Voyager 2, launched August 20th, 1977, before its sister spacecraft. Despite the numbering, it embarked on the Grand Tour using a rare planetary alignment to visit Jupiter, Saturn, Uranus, and Neptune. In a single trajectory, it remains the only spacecraft ever to have visited Uranus and Neptune. It crossed the heliopause in November 2018, officially entering interstellar space, and is currently the second most distant human-made object, approximately 135 AUP from the Sun. And uniquely among our 5, it is still communicating with Earth. Voyager 1, launched September 5th, 1977, 2 weeks after Voyager 2, despite being numbered first. It visited Jupiter and Saturn, made the first detailed observations of Saturn's moon Titan, and then was directed on a trajectory that would take it up and out of the plane of the solar system. It crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. It is the most distant human-made object in existence. As of 2026, it is approximately 165 ATU from the Sun, about 15 billion miles. And it is still transmitting. Its signals, traveling at the speed of light, take more than 22 hours to reach us. New Horizons, launched January 19, 2006. It was designed primarily to explore Pluto, which it did on July 14, 2015. The first spacecraft ever to fly past Pluto, revealing a world of stunning complexity that had been a blurry dot in every telescope ever pointed at it. After Pluto, it continued into the Kuiper Belt, flying past the object Arakoth in January 2019. It is now approximately 60 AU from the Sun, and still operating. It has not yet reached the termination shock, but it is heading in that direction. In the decades ahead, it too will cross the heliopause and enter interstellar space. 5 spacecraft, 5 stories, decades of silence from 2 of them, 3 still alive, all still moving. Let's go back to the beginning. Pioneer 10. The first, it is March 2nd, 1972. The Cold War is still very much a reality. Apollo 16 hasn't launched yet. The Watergate break-in is still months away. And a rocket lifts off from Cape Canaveral, carrying a spacecraft smaller than a car, designed to do something that had never been done. Travel through the asteroid belt and make direct observations of Jupiter. The asteroid belt had a reputation, somewhat overstated as it turned out, for being a hazardous place. Popular imagination pictured it as a dense field of tumbling rocks, dangerous to navigate. Nobody knew for certain what Pioneer 10 would encounter as it crossed that region of space. Mission planners had done their calculations and believed it was probably survivable. But the only way to know was to go. Pioneer 10 went. The asteroid belt turned out to be navigable, The rocks are real, but the distances between them are vast. The spacecraft passed through without incident, confirming what the math had suggested, that the image of a dense, impassable rock field was a fiction. Future missions to the outer planets could follow. Jupiter was another matter. Pioneer 10 reached Jupiter in December 1973. The closest approach was about 82,000 miles from the cloud tops, close enough to detect, measure, and be affected by things that no instrument in Earth orbit could observe. What it found at Jupiter was extraordinary. Jupiter's magnetic field is enormous, not just larger than Earth's in the way a planet that's 1,300 times our volume might be expected to have a larger field. Enormous in a way that defied easy intuition. Jupiter's magnetosphere, the region of space dominated by its magnetic influence, extends roughly 600,000 miles in the direction of the Sun, and millions of miles in the opposite direction, forming a vast magnetotail stretched out by the solar wind. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear larger than the full moon in our sky. It is the largest structure in the solar system, dwarfing the Sun itself in extent, though not in mass or energy. Pioneer 10 flew through this magnetosphere and measured it directly. The radiation environment inside was intense, far more intense than mission planners had anticipated. The spacecraft's instruments detected radiation doses that would have been lethal to an unprotected human in a matter of hours. Jupiter, it turned out, was surrounded by a vast belt of trapped charged particles, similar to Earth's Van Allen belts, but incomparably more energetic and extensive. Any future human mission to Jupiter would have to take this radiation environment seriously. Pioneer 10 taught us that Jupiter is, in terms of radiation, among the most hostile environments in the solar system. It also confirmed something that had been theorized but never directly observed. Jupiter has no solid surface. Its atmosphere is a gradual transition from gas to liquid to, at sufficient depth, possibly metallic hydrogen, a state of matter in which hydrogen, compressed to extreme pressures, becomes an electrical conductor. There is no ground to land on. Jupiter is a world of infinite depth, of crushing pressure, of winds that move at hundreds of miles per hour across a surface area larger than all the inner planets combined. Jupiter's Great Red Spot, a storm that had been observed through telescopes since the 1600s, was directly imaged by Pioneer 10. The storm's scale became clearer. It is large enough to contain 2 or 3 Earths inside its circulation. It is not a temporary weather event. It is a permanent feature, a self-sustaining atmospheric vortex that has been rotating for at minimum hundreds of years, and possibly much longer. Pioneer 10 also measured Jupiter's heat output. Jupiter radiates more heat than it receives from the Sun. It is generating its own internal heat through gravitational compression, slowly contracting under its own immense gravity and converting that gravitational potential energy into thermal energy. Jupiter is not a star. It doesn't have the mass to sustain nuclear fusion, but it is something in between, a world that generates energy from within, rather than purely absorbing it from outside. This changes how we think about Jupiter. It is not a cold, passive outer planet. It is, in a limited sense, active. After Jupiter, Pioneer 10 continued outward, past the orbit of Saturn, past Uranus, past Neptune, beyond Pluto, into the region where no spacecraft had ever been. And it kept going. For decades, engineers at NASA's Jet Propulsion Laboratory tracked Pioneer 10's position and velocity with extraordinary precision. using radio timing techniques that could measure the spacecraft's speed to a fraction of a millimeter per second. And something was wrong. The Pioneer anomaly. Pioneer 10 was slowing down. Not by much. The deceleration was small, but it was measurable, and it was consistent. And it was not predicted by Newton's laws or Einstein's general relativity. The gravitational influences of the Sun and the planets had been accounted for with extreme precision. Solar radiation pressure, the tiny push of photons from the Sun against the spacecraft's surface, had been modeled. The outgassing of residual gases from the spacecraft had been estimated. Everything that should cause a drift in the trajectory had been calculated, and the numbers didn't add up. Pioneer 10 was experiencing a tiny, unexplained acceleration directed back toward the Sun. Not enough to stop it or slow it dramatically, but a persistent, consistent deviation from the predicted path. When the same analysis was applied to Pioneer 11, it showed the same anomaly. Both spacecraft, heading in opposite directions out of the solar system, were experiencing the same tiny, unexplained pull toward the Sun. This became known as the Pioneer anomaly, and for roughly a decade, it attracted serious scientific attention. The anomaly was small. The unexplained acceleration was roughly 8 times 10 to the negative 10 meters per second squared. That is an almost incomprehensibly tiny force. In practical terms, after 10 years of travel, the cumulative effect had moved the spacecraft about 400,000 kilometers from where the equations said it should be. Significant enough to measure, small enough to be caused by almost anything, which was part of the problem. The list of possible explanations that serious physicists put forward was extensive. There were mundane engineering explanations. Heat radiating unevenly from the spacecraft's onboard nuclear power source could create a tiny thrust. Unmodeled gas leaking from the spacecraft could push it. Electromagnetic forces from onboard systems could interact with the solar magnetic field. There were less mundane explanations. Dark matter in the solar system creating a gravitational effect. Some modification to Newtonian gravity at very long distances, a property of space-time that general relativity didn't fully capture. Even a hint, whispered only half seriously in some corners, of something genuinely new in physics. For over a decade, the Pioneer anomaly was a genuine open question in physics. Papers were written, conferences were held. The possibility that it represented new physics, that Newton and Einstein needed revision at solar system scales, was seriously entertained. The resolution came in 2012 and 2013, when a team of researchers completed a thorough reanalysis of the Pioneer's thermal environment. Using recovered archival data about the spacecraft's heat output, data that had not been fully incorporated into earlier analysis, they modeled, with much greater precision than before, the heat radiated by the Pioneer's radioisotope thermoelectric generators, the RTGs, which were the onboard nuclear power sources. The RTGs generate heat. That heat radiates in all directions, but not perfectly symmetrically. The geometry of the spacecraft meant that slightly more heat was radiated in the backward direction than in the forward direction. Heat is photons. Photons carry momentum. Slightly more photons going backward means a slightly net forward force. Except the spacecraft was heading away from the Sun. Forward, for Pioneer 10, was away from the Sun. The net thermal radiation pressure was directed away from the Sun. But the anomaly was an acceleration toward the Sun. Wait, the geometry requires closer attention. The RTGs were mounted on long booms behind the spacecraft's main dish antenna. The main dish was pointed back toward Earth to maintain communication, which, given that Pioneer 10 was heading roughly away from Earth, meant the dish was roughly facing the sun. The thermal radiation from the RTGs hitting the back of the dish was reflected forward, toward the sun. The spacecraft was being nudged, very slightly, back toward the sun by its own waste heat, reflecting off its own antenna. This is delicate work, accounting for the exact geometry of the spacecraft, the temperature distribution across every surface, the reflectivity of every material, the slow change in these parameters as the spacecraft aged and the RTGs cooled. All of it feeding into a prediction that matches the observed anomaly. When the thermal analysis was complete, the residual anomaly essentially disappeared. The Pioneer anomaly was thermal recoil force. Not dark matter, not new physics, not a failure of general relativity. The universe's fundamental laws, as currently understood, survived the Pioneer anomaly intact. But the story illustrates something important about doing science at the edge of the solar system. At those distances, everything matters. Every tiny force, every watt of heat, radiating in every direction, every detail of spacecraft geometry accumulates into measurable effects over years and decades. The solar system is not empty. And, even in its most remote reaches, the precision required to understand what you're measuring demands that you account for things that seem, in any normal engineering context, negligibly small. Pioneer 10's last confirmed signal arrived at Earth on January 22, 2003. The spacecraft was approximately 12 billion kilometers from the Sun, 80 ATU, and its RTGs had degraded to the point where the signal was too faint for the receiving dishes to detect reliably. NASA made several more attempts to contact Pioneer 10 in subsequent months. No response was ever confirmed. It is not broken. Nothing catastrophic happened. It simply went too far. The signal became too quiet for our ears. Pioneer 10 is still out there, still moving at roughly 27,000 miles per hour, on a trajectory that takes it in the direction of Aldebaran, a red giant star about 65 light-years away. In roughly 2 million years, if nothing deflects it, it will pass through the general region of that star. No one will be here to know. Attached to its structure, like a message in a bottle thrown into an incomprehensibly large ocean, is a gold anodized aluminum plaque, 9 inches by 6 inches, engraved with images. A diagram of the hydrogen atom, the most common element in the universe, a natural unit of measurement, and a statement that whoever made this understood atomic physics. A pulsar map, showing the position of the Sun relative to 14 pulsars, each labeled with their characteristic period. Pulsars are natural beacons, rotating neutron stars that emit precise radio pulses, like cosmic lighthouses. Any civilization advanced enough to receive the spacecraft would presumably know the pulsars of their own galaxy, and the map gives the position of the Sun in relation to them. In principle, the Sun can be located from the plaque if you know the galaxy. A diagram of the solar system, showing the trajectory of Pioneer 10 past Jupiter and outward. And 2 human figures, a man and a woman, drawn in silhouette against the outline of the spacecraft for scale. The man's right hand is raised in greeting, a gesture of open-handed non-aggression, the closest thing to a universal greeting that the designers could think of. Together, they represent a species. Not any specific culture, not any specific body type, but a reasonable generalization of what a human being looks like, rendered in simple lines on a small metal plate hurtling through the dark. Carl Sagan, who was part of the team that designed the plaque, described it as a message in a bottle cast into the cosmic ocean. The odds of it ever being found are extraordinarily low. It will drift for billions of years through the void between stars, almost certainly never encountering anything solid. The galaxy is mostly empty space. The chance of any other civilization intersecting with a spacecraft smaller than a car over the span of billions of years, in a galaxy 100,000 light-years across, is vanishingly small. But it is not zero. And there was something in the people who designed it that felt the gesture was worth making anyway, not as a practical communication strategy, as a statement about who we are, about the kind of species that, when it sends something into the dark, puts a hand-raised figure on it, just in case. Pioneer 11, the one that went both ways. Pioneer 11 launched in April 1973, just over a year after Pioneer 10. Its mission profile was similar, but more ambitious. It would visit Jupiter like its predecessor, but instead of continuing directly outward, it would use Jupiter's enormous gravitational field as a slingshot to redirect itself toward a second destination: Saturn. This was the first time such a trajectory had been used for an outer planet mission. The gravity assist maneuver, flying close to a massive planet, stealing a tiny fraction of that planet's orbital energy, and using it to accelerate and redirect the spacecraft, was becoming a recognized technique in mission planning. Pioneer 11 demonstrated that a single spacecraft could be retargeted using gravity rather than fuel, visiting multiple destinations on a single launch. Jupiter, again, proved formidable. Pioneer 11 flew much closer than Pioneer 10 had, within about 21,000 miles of the cloud tops, putting it deep inside the radiation belts that Pioneer 10 had mapped. Mission engineers accepted this risk deliberately, using the experience of Pioneer 10 to understand what the radiation environment would do to the spacecraft. The risk paid off. Pioneer 11 survived and acquired detailed new measurements of Jupiter's magnetic field, atmosphere, and interior. Then it swung south of the plane of the solar system and arced outward towards Saturn. It arrived at Saturn in September 1979, the first spacecraft ever to make direct observations of the sixth planet. What Pioneer 11 found at Saturn changed our understanding of the planet's ring system in a fundamental way. Saturn's rings had been observed through telescopes for centuries. Since Galileo first noted in 1610 that Saturn appeared to have strange appendages, a misshapen appearance he couldn't explain with the telescopes of his era. By the mid-1600s, it was understood that the rings were a flat disk of material surrounding the planet. By the 19th century, astronomers had identified multiple distinct rings and ring gaps, with names like the Cassini division, the most prominent gap between the A and B rings. But Pioneer 11 found something the distant telescopes couldn't see. A new ring. Designated the F ring, it sits just outside the A ring, in a region that had previously appeared clear. It is a narrow, braided, strangely structured ring, unlike the broad, smooth rings visible from Earth. Its narrowness and unusual structure were puzzling. The ring seemed more complex than a simple collection of orbiting debris. Later missions would reveal that the F ring is kept narrow and shaped by two small moons on either side of it, called shepherd moons. The moon's gravitational influence confines the ring material, preventing it from spreading. Pioneer 11 discovered the ring. Voyager would later provide the understanding. Pioneer 11 also discovered two new moons of Saturn, small bodies that hadn't been detected from Earth, and confirmed the existence of Saturn's magnetosphere, which, unlike Jupiter's, is nearly perfectly aligned with the planet's rotation axis. Saturn's magnetic field is unusual among the solar system's planets in this regard, and why it's so symmetrically aligned remains a question that planetary scientists continue to investigate. After Saturn, Pioneer 11 headed in a direction roughly toward the center of the galaxy, in the constellation Aquila. Its last signal was received in November 1995. The spacecraft was about 6.5 billion kilometers from the Sun, and its power had degraded to the point where communication was no longer possible. Pioneer 11 has been silent for more than 30 years. It carries the same golden plaque as Pioneer 10. The same man and woman, the same hydrogen diagram, the same pulsar map, going in a different direction, into the same dark. Voyager 2, the Grand Tour. Let's talk about a window in time. In the late 1960s, a young engineer at NASA's Jet Propulsion Laboratory, named Gary Flandreau, was doing trajectory calculations for potential outer solar system missions. He noticed something remarkable in the orbital mechanics. Every 175 years, approximately, the outer planets of the solar system align in a configuration that makes something theoretically possible that, at other times, is practically impossible. Not a perfect geometric alignment. They don't line up like beads on a string, but a configuration in which the planets are arranged in a rough arc, such that a spacecraft launched in the right direction at the right time could use each planet's gravity to slingshot to the next, visiting all 4 giant planets: Jupiter, Saturn, Uranus, and Neptune, in a single continuous mission. The next such window opened in 1977. After that, it would close. The next similar alignment would not occur until the mid-2150s. The window was real, but it required action. A mission would have to be planned, funded, built, and launched. The spacecraft would have to be ready. It was. This was the Grand Tour, and the spacecraft that would fly it were the Voyagers. 2 of them, launched 16 days apart, in August and September of 1977. Voyager 2 went first, on August 20th. Voyager 1 went second, on September 5th, but on a faster trajectory that would cause it to reach Jupiter and Saturn before its sister craft. Hence the naming. The Voyagers were more sophisticated than the Pioneers in almost every way. They carried larger, more capable scientific instruments. They were designed to return images of far higher quality. They were optimized for exactly the kind of multi-target, multi-year mission that the Grand Tour required. And they would reveal the outer solar system as it had never been seen. Voyager 2 reached Jupiter in July 1979. What it found there went far beyond what the Pioneers had shown. The first image that will stop you, even now, even decades later when we've seen so many extraordinary things from space, is Io. Io is one of Jupiter's 4 large Galilean moons. The moons large enough that Galileo could observe them in the 1600s with his primitive telescope. It was expected, going in, to be something like our moon. A cold, cratered, dead world. A ball of rock and ice, pockmarked by ancient impacts. Geologically inert. The first close images from Voyager 1, which reached Jupiter a few months before Voyager 2, showed something completely unexpected. Io was not cratered. It had almost no impact craters at all. Its surface was an alien landscape of yellows and oranges and reds and whites, covered in what appeared to be sulfur compounds, utterly unlike any other body in the solar system. A scientist named Linda Morabito examining images of Io looking for background stars, noticed an umbrella-shaped protrusion extending from the limb of the moon. It was a volcanic plume. Io was actively erupting. A volcano on Io was ejecting material 300 kilometers into space, while the spacecraft was watching. Io is the most volcanically active body in the solar system. More volcanic activity per unit of surface area than anywhere else we have ever found, including Earth. The reason is tidal heating. Io orbits Jupiter in an orbital resonance with two other large moons, Europa and Ganymede, which keeps its orbit slightly elliptical. As Io moves closer to and farther from Jupiter in its orbit, Jupiter's immense gravity squeezes and stretches it, kneading it like dough, generating heat through friction. That heat drives volcanic activity so intense that the entire surface of Io is recycled every few million years by its own eruptions. There are no old craters, because any crater is quickly buried or erased. This discovery alone, that tidal heating can power geological activity on bodies far from the sun, far from any internal radioactive heat source, completely changed how scientists thought about the possibility of geological and potentially biological activity in the outer solar system. If Io can be volcanically active from tidal heating, then other moons might be geologically active too. Europa, Ganymede, and Enceladus. Around Saturn, tidal heating becomes a relevant energy source for the outer solar system, not just for bodies near the Sun. Voyager 2 also got a close look at Europa, the smoothest body in the solar system. Europa's surface is ice, water ice, crossed by a network of brown cracks and ridges, but otherwise almost featureless. The absence of craters on Europa's ice surface suggested the ice was being continuously renewed, not by volcanoes, but by an ocean of liquid water beneath. Tidal heating was keeping water liquid underneath an icy shell, and that liquid water was periodically resurfacing, freezing, covering old craters. Europa might have a subsurface ocean with more liquid water than all of Earth's oceans combined. The possibility of life in that ocean, under the ice, warmed by tidal heating, in liquid water that has been liquid for potentially billions of years, was not lost on anyone. Voyager 2 spent only a brief time at Jupiter before its trajectory carried it onward towards Saturn. Saturn in November 1980 for Voyager 1 and August 1981 for Voyager 2. Between the two Voyager encounters and the earlier Pioneer 11 data, Saturn was explored in extraordinary detail. The ring system, resolved into thousands of individual bands and structures rather than the handful visible from Earth. Shepherd moons. Gaps in the rings caused by orbital resonances with Saturn's moons. The braided F-ring. Saturn's moon Titan was a particular focus of Voyager 1, which flew close enough to measure Titan's atmosphere directly. What it found was a dense, hazy atmosphere of nitrogen and methane, with complex organic chemistry happening in the upper layers. Titan has a surface pressure 1.5 times Earth's atmospheric pressure. It is the only moon in the solar system with a substantial atmosphere. Its surface was hidden beneath an orange haze too opaque for Voyager's cameras to penetrate. That would have to wait for a later mission. But the chemistry was astonishing. Titan was a laboratory for the kind of organic chemistry that preceded life on Earth, playing out in slow motion on a frozen world in the outer solar system. After Saturn, Voyager 1 was directed on a trajectory that took it up out of the plane of the solar system, ending any possibility of visiting Uranus or Neptune. It was pointed toward interstellar space and left to travel. Voyager 2 continued on the grand tour. Uranus, January 1986. The only spacecraft that has ever visited the seventh planet. Uranus is strange in a way that no other planet quite is. While every other planet in the solar system rotates roughly upright, their poles pointing more or less perpendicular to the plane of their orbits, Uranus is tipped almost entirely on its side. Its axial tilt is 98 degrees. It doesn't rotate so much as it rolls along its orbital path, like a bowling ball moving around the sun. One pole faces roughly toward the sun for half of the planet's 84-year orbit. Then the other pole faces the sun for the other half. The cause of this is thought to be a massive ancient collision, something very large hitting Uranus early in its history and tipping it over. What exactly that something was is not known with certainty. What Voyager 2 found at Uranus was, in some ways, surprisingly quiet. The planet's atmosphere was relatively featureless compared to Jupiter's dramatic bands and storms. Its winds blow at speeds up to 560 miles per hour, but the upper atmosphere is hazily uniform, tinted a pale blue-green by methane-absorbing red light. No great storm like Jupiter's red spot. No bands of dramatically different colors. Uranus's rings, discovered in 1977 from Earth when the planet passed in front of a star and blocked its light, were resolved by Voyager 2 into 10 distinct rings, narrow and dark, utterly unlike Saturn's broad, bright rings. Where Saturn's rings are composed primarily of water ice and are highly reflective, Uranus's rings are composed of darker material and reflect very little light. They are subtle, hard to see, easier to detect in silhouette than in direct reflection. Voyager 2 also discovered 10 new moons of Uranus, bringing the known total to 15. These moons, closer to the planet than the larger moons already known, had gone undetected from Earth because of their small size and proximity to the planet's glare. Perhaps the most remarkable thing about Uranus in retrospect is this. By the time Voyager 2 left it, we had visited it exactly once, in January 1986. And as of this writing, that is still the only time. No other spacecraft has visited Uranus. No orbiter, no probe, no follow-up mission. The planet that rolls on its side, with its dark narrow rings and its unexplained tilt, has been visited once by a spacecraft that spent hours passing through its system and then kept going. Everything we know about Uranus in close-up detail comes from a spacecraft that flew by in the month that the Challenger space shuttle was destroyed. Voyager 2 ate Neptune, the last planet, August 1989. 12 years after launch, Voyager 2 made its closest approach to Neptune, the last of the four gas giants, the most remote planet in the solar system. Neptune was, in some ways, the biggest surprise of the entire Grand Tour. Going in, expectations were modest. Voyager 2 had to be redirected somewhat to fly close to Neptune's large moon Triton, which was considered potentially interesting. The encounter geometry meant less time near the planet itself, fewer images, more restricted data. After the quiet surprise of Uranus, perhaps Neptune would be similarly featureless. It wasn't. Neptune's atmosphere was dynamic in a way Uranus's had not been. The cameras revealed a large, dark oval in the southern hemisphere, immediately named the Great Dark Spot, by analogy with Jupiter's Great Red Spot. The storm was comparable in size to Earth. Its winds, measured from the movement of cloud features, were blowing at roughly 1,500 miles per hour, the fastest winds recorded on any planet in the solar system at that time, fast enough to circle Earth in less than 2 hours. The Great Dark Spot was a hurricane-scale atmospheric vortex on a planet receiving only about 1/900th of the sunlight Earth does. Neptune generates its own internal heat, like Jupiter. But even accounting for that, the energy available for driving such intense atmospheric circulation seemed surprising. Neptune is still not fully understood in terms of what drives its atmospheric dynamics. There were also smaller, fast-moving white cloud features, which Voyager 2 tracked over the course of the flyby. One of them, named Scooter, moved much faster than the large storm feature, completing a circuit of the planet in about 16 hours. The variety of atmospheric features, the coexistence of the slow large storm and the fast small clouds, spoke to a complexity that the outer planet had been hiding behind its blue serenity. Neptune's rings were confirmed, thin, incomplete arcs, patchy in their distribution around the planet, in a way that had been puzzling from Earth-based observations. Voyager 2 showed why. The rings are not uniform, but clumped into denser and thinner sections, creating the appearance of arcs rather than complete rings. The gravitational influence of nearby small moons shapes the clumping. And then there was Triton. Triton is one of the strangest objects in the solar system. It orbits Neptune in the wrong direction, retrograde, meaning it orbits opposite to the planet's rotation. Every other large moon in the solar system orbits in the same direction its planet rotates. Triton's retrograde orbit is unique among large moons, and is almost certainly evidence that it is a captured object, a body that originally formed elsewhere in the outer solar system, perhaps in the Kuiper Belt, and was captured by Neptune's gravity at some point in the distant past. A captured moon cannot maintain a circular orbit indefinitely. The tidal forces from the planet will slowly circularize and then decay the orbit. Triton is spiraling inward, extremely slowly. In roughly 3.6 billion years, it will either be torn apart by Neptune's tidal forces and create a new ring system, or it will collide with Neptune. It is, in a sense, doomed on a geological timescale. When Voyager 2 flew past Triton, it photographed a world of extraordinary strangeness. Triton's surface temperature is about -235 degrees Celsius, making it the coldest measured surface in the solar system. It is so cold that nitrogen, which is a gas in Earth's atmosphere, freezes solid on Triton's surface. The poles are covered in nitrogen ice and frozen methane. But the most remarkable thing Voyager 2 found on Triton was not the ice. It was geysers. Active nitrogen geysers erupting from the surface, dark, streaky plumes of nitrogen gas, and dark particles being ejected from the surface and carried downwind by Triton's thin atmosphere. Erupting from a world so cold that nitrogen freezes solid. The mechanism was understood quickly. Triton's southern polar cap of nitrogen ice, illuminated by weak sunlight, absorbs enough solar energy through the transparent ice to vaporize nitrogen at the base of the ice cap. The gas pressure builds until it erupts through weak spots, creating geysers that shoot material several kilometers into the sky. Active geology, of a sort, on a world at -235 degrees Celsius, lit only by a sun so distant it appears just another bright star. After Neptune, Voyager 2 continued on a trajectory that would eventually carry it across the heliopause and into interstellar space. The cameras, by the time of the Neptune encounter, had already been doing their final significant work. After Neptune, the solar system had no more planets to visit. The outer dark beckoned, but before Voyager 1 disappeared completely into that dark, it did something unusual. At the suggestion of Carl Sagan, mission scientists turned Voyager 1's cameras around for one last look. The year was 1990. The spacecraft was about 6 billion kilometers from the Sun, roughly 40 HU, high above the plane of the solar system. The cameras were pointed back toward the inner solar system and took a series of images. Those images were assembled into a mosaic, a portrait of the solar system from outside. In it, Earth appears as a single pixel of light, a pale blue dot, less than 1/12 of a pixel in diameter, suspended in a sunbeam that crossed the frame due to light scattering inside the camera. Carl Sagan, who had pushed for the image to be taken, wrote about it. The point he made about everything our species has ever done and built and fought over and loved, existing on that single pixel. That is not a metaphor. It is a literal description of what the image shows. From 40 AU, the Earth is a dot. From where our 5 spacecraft are now, 60, 105, 135. 135, 165 AU from the Sun. The Earth is invisible, not a faint point of light, not a pixel, below the threshold of detection entirely, lost in the glare of the Sun. We are out there, but Earth is not visible to them anymore. Our world has gone below the horizon of what can be seen. What the Voyagers carry, the golden record. In 1977, when the Voyagers were being prepared for launch, Carl Sagan led a committee charged with a task that sounds simple and is anything but. Create a message from humanity, something to attach to the spacecraft, to send with them into the dark, to represent what we are and what we know, and what we value to any civilization that might one day find them. Not a plaque this time, a record. A golden phonograph record, 12 inches in diameter, gold-plated copper, designed to last 1 billion years in the vacuum of space. On it, encoded in audio and visual formats, would be a message, the most carefully considered message humanity has ever composed. The committee had roughly a year to work with, a year to decide what a civilization from another star system should know about us, if they found us after we were gone. The record begins with spoken greetings in 55 human languages, ranging from Akkadian, a dead language of ancient Mesopotamia, to Wu Chinese. Each greeting is brief. A few words, a sentence. Hello. Peace to all who inhabit this universe. We offer friendship across the stars. They cover the arc of human linguistic history from the ancient to the contemporary. A choir of human voices speaking into the dark in the full range of ways humans have learned to speak. There are sounds from Earth. The sound of surf breaking on a shore, rain, wind, thunder, the sounds of animal life, birds, frogs, elephants, whales, dogs, footsteps on gravel, laughter, a mother and child, the sound of a kiss, fire, a train, a rocket launching from Earth, the kind of sounds that could only exist in a world with atmosphere and liquid water and biology. There is music, 90 minutes of it, drawn from across human cultures and human history. Johann Sebastian Bach's Brandenburg Concerto No. 2 in F major. Sagan reportedly included it because, if we were going to brag, we might as well brag properly. Chuck Berry's Johnny B. Good. Traditional music from Senegal, Zaire, Australia, Japan, India, Azerbaijan, Peru, Bulgaria, and many others. Beethoven, Stravinsky, Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a wordless slide guitar blues recorded in 1927. one of the most haunting sounds in all of American music, chosen because it expressed human loneliness in a way that seemed, somehow, universal. There are 116 images encoded on the record, translated into audio signals that can be reconstructed into pictures. The images include the mathematical constants that define our physical universe, so that the recipient knows the encoding system, anatomical diagrams of a man and woman, images of human beings from around the world, children, elderly people, people eating and running and working and loving, landscapes from every continent, the Great Wall of China, the Sydney Opera House, photographs of human food, human shelter, human traffic, human technology, a diagram of the solar system, an image of Earth from space. Instructions for playback are engraved on the record's cover in diagrammatic form, without assuming any knowledge of human notation or language. The format for converting the audio signals into images is shown. The rotation speed is indicated. The pulsar map showing the position of the sun is included, as on the Pioneer plaques. The record also contains a message from the Secretary-General of the United Nations at the time, Kurt Waldheim, and a recording of the brainwave patterns of Ann Druyan, Sagan's collaborator and eventual wife, recorded while she thought deliberately about the history of Earth and the nature of being human. Her neural activity, translated into audio, is on the record. In some sense, she is on the record, thinking human thoughts about human things, encoded in gold, traveling between stars. Sagan described the golden record as a bottle cast into the cosmic ocean. The odds of it ever being found are extraordinarily low. The Voyagers are traveling at roughly 35,000 miles per hour, fast by any human standard, but negligibly slow against the scale of interstellar distances. In 40,000 years, Voyager 1 will pass within about 1.7 light-years of the star Gliese 445. It will not enter that star's planetary system. It will simply pass through the general vicinity and continue. The record on each spacecraft has a conservative estimated survival time of 1 billion years in the vacuum of space, protected from radiation by the spacecraft itself. 1 billion years. In 1 billion years, our sun will have brightened enough to have made Earth uncomfortably warm for complex life. Whatever exists on Earth in 1 billion years, if anything does, will be as different from us as we are from the first multicellular organisms. Our civilization will be a geological artifact, its physical traces barely distinguishable from natural processes. And the Voyagers will still be out there, still carrying their records, still moving, slower now. The sun's gravity will have reduced their speeds further, but still moving. The golden record is the most durable thing humanity has ever made. Not in terms of material. We have made things from materials with longer physical half-lives, but in terms of what it is designed to outlast. It is designed to outlast our civilization, to speak to whoever comes after us, or whoever finds us from somewhere else, about what we were while we were here. There is something in that gesture, the act of sending a record of ourselves into a billion-year future. Not for any practical purpose, not because we expected to accomplish anything, but because we felt it mattered. That tells you something important about what kind of species we are. We are not only practical, we are not only forward-looking in a strategic sense. We also reach backward and upward simultaneously, into time and into space, wanting to be known by someone, wanting to leave evidence of having been here, wanting the universe to know that something inside it briefly became aware of itself and found it beautiful. That is the golden record. Not a manual, not a treaty. A gift, sent at the speed of 35,000 miles per hour, into the dark between stars, to whoever might one day find it. Let's pause here and sit with something for a moment before we move forward. Right now, as you're listening, 2 of these 5 spacecraft are transmitting. Voyager 1 and Voyager 2 are still sending signals back toward Earth. Signals traveling at the speed of light, the fastest thing the universe permits, and still taking more than 22 hours for Voyager 1's signal to arrive. The engineers at NASA's Deep Space Network listen to them still. They maintain an active relationship with spacecraft launched almost 50 years ago. Hardware running on technology that predates the personal computer, power sources slowly dying, instruments slowly failing, but still talking. The signal from Voyager 1, by the time it reaches Earth, is so faint that receiving it requires some of the largest dish antennas on the planet. The signal power arriving at Earth from Voyager 1 is approximately 20 billion times fainter than the power used by a standard digital watch. 20 billion times fainter. And yet, we can hear it. In 2023, engineers lost the ability to interpret Voyager 1's science data for several months due to a computer memory corruption issue. One of 3 onboard computers with a combined memory of roughly 69 kilobytes, less than a single small image file on a modern phone, had developed a problem that was scrambling its output. Engineers on Earth, working with hardware nearly 165 AU away, with a 22-hour round-trip communication delay, diagnosed the problem, developed a fix, and uploaded new code to a spacecraft more distant than any object humans have ever built. It worked. Voyager 1 resumed transmitting usable data in April 2024. This is not a small thing. This is people in California talking to a spacecraft 15 billion miles away, fixing a computer problem from the other side of the solar system, on hardware built in the 1970s. Still working, the people who built Voyager 1 could not have imagined that anyone would still be talking to it in 2024. The mission was designed for a 5-year lifespan. It is now past 48 years. There is one more spacecraft in our 5 that we haven't yet fully explored. New Horizons, launched in 2006, is the youngest of the 5 and the only one designed and built in the era of modern computing. It is heading for the Kuiper Belt and beyond, carrying a scientific payload more sophisticated than anything the Pioneers or Voyagers carried. And it has already made one discovery that, in terms of sheer visual impact, rivals anything the Grand Tour produced. That discovery, and the deeper story of what New Horizons found at the edge of the solar system, is what we'll explore when we continue this journey. For now, let's hold what we've learned tonight. 5 objects, all still out there, all still moving. Pioneer 10, silent since 2003, carrying its golden plaque toward a star it will pass in 2 million years. Pioneer 11, silent since 1995, heading in the opposite direction, carrying the same message. Voyager 2, still transmitting, now in interstellar space, the only spacecraft to have visited all 4 outer planets, carrying its golden record toward whatever comes next. Voyager 1, still transmitting, further from Earth than any human-made object in history, also in interstellar space, also carrying its record, listening to a universe that has been silent back at us since the moment it arrived. And New Horizons, still approaching the edge of the heliosphere, carrying knowledge of Pluto that no instrument had carried before it. January 19th, 2006, a rocket lifts off from Cape Canaveral in Florida, carrying the fastest spacecraft ever launched. New Horizons, an instrument-packed probe roughly the size and shape of a grand piano, was launched on a trajectory so energetic that it crossed the orbit of the Moon in 9 hours. The Apollo missions took 3 days to cover the same distance. The mission's target was Pluto, a world that, when New Horizons launched, had just barely been demoted from planetary status. In August 2006, 7 months after launch, the International Astronomical Union voted to reclassify Pluto as a dwarf planet, a member of the newly defined category of smaller round bodies in the outer solar system, rather than a full planet. The demotion was not popular with the general public, which had grown attached to Pluto across the 76 years since its discovery. But it was scientifically reasonable. Pluto is one of many similar bodies in the Kuiper Belt. Large but not uniquely large, not gravitationally dominant in its neighborhood, the way the 8 recognized planets are. None of this changed what New Horizons was going to find there. Pluto had been, before July 2015, a blur. The best images ever made of it before the flyby came from the Hubble Space Telescope and showed Pluto as a smudged, pixelated disk, with vague light and dark regions but no detail. After 67 years of knowing Pluto existed, we could not clearly see its surface. It was too small, too far, too dim. We knew its size, roughly 2,370 kilometers in diameter, making it smaller than our moon. We knew its mass. We knew it had a thin nitrogen atmosphere that partially froze out when Pluto moved to the far end of its elliptical orbit, away from the Sun. We knew it had moons, 5 of them, the largest named Charon. Discovered in 1978 and large enough relative to Pluto that the 2 bodies orbit their common center of mass in empty space between them, making them more like a binary system than a planet and moon in the traditional sense. What we didn't know was what Pluto actually looked like, what was on its surface, what its atmosphere was doing, whether it was geologically alive or dead, whether it was boring or extraordinary. New Horizons would take 9 years to get there. 9 years of interplanetary crews, of instrument checkups and course corrections, and annual hibernation periods to conserve power, while the spacecraft hurtled through the outer solar system at speeds approaching 50,000 kilometers per hour. 9 years of waiting. The science team, the people who had conceived the mission, built the instruments, written the proposals, survived the budget battles that nearly cancelled New Horizons multiple times during development, waited 9 years to learn what was on Pluto. As New Horizons approached in the early months of 2015, the images began arriving. First, just smudges slightly less blurry than Hubble. Then, by late spring, details started to resolve. Strange patterns on the surface. A bright region in the lower left of the disk. Darker regions elsewhere. Something was there. Something with structure. Something more complex than a uniform icy ball. By early July 2015, the images were good enough to provoke genuine excitement among the science team. There were mountains, that much was clear. Mountains casting shadows in the oblique sunlight, their heights determinable from the shadow lengths. Mountains on a world that, at the distance of Pluto from the Sun, receives about 1,000 times less sunlight than Earth. Mountains in the dark. And then, 6 days before closest approach, something else became visible. The bright region, the one that had shown up as a vague smear in the earliest resolved images. As the resolution improved, it revealed itself to have a distinctive shape. A heart, a vast, roughly heart-shaped plain of brilliant white, nearly the size of Texas and Oklahoma combined, dominating a large portion of Pluto's face. Smooth, reflective, bright enough to dominate the planet's appearance from millions of miles away. The science team named it informally after Clyde Tombaugh, the astronomer who discovered Pluto in 1930. Tombaugh Regio, the heart. And on July 14, 2015, New Horizons made its closest approach. A flyby at 12,500 kilometers above Pluto's surface, moving so fast that the entire close encounter lasted only minutes. The flyby. There was a problem with July 14th. Not with the spacecraft, with the timing. New Horizons, during closest approach, was too busy collecting data to transmit it. The spacecraft was pointed at Pluto, not at Earth, using every instrument to capture everything it could about a world it would pass only once and never return to. The data was stored on board. The transmission would come later. After closest approach, the spacecraft executed a turn and began transmitting. But the data would take hours to arrive, and it would continue arriving, piece by piece. For the next 16 months, because the volume of data New Horizons had collected, images, spectroscopy, particle measurements, atmospheric profiles, surface composition maps, exceeded what could be transmitted quickly over the faint radio link across 7.5 billion kilometers of space. At the data rate achievable from that distance, transmitting everything required the better part of a year and a half. The team waited at the Applied Physics Laboratory in Laurel, Maryland, for the signal that would confirm the spacecraft had survived. New Horizons was designed to fly autonomously during the encounter, making its own decisions in real time because the communication delay, the one-way light travel time, was about 4.5 hours, made ground control impossible during the actual flyby. Whatever happened, happened, and they wouldn't know for hours. At 8:52 p.m. on July 14, 2015, the signal arrived. New Horizons was alive. The flyby had succeeded. The images that followed over the next several days rewrote what we knew about the outer solar system. The mountains were the first surprise. Not just any mountains, enormous ones. Ridges of water ice rising 3,500 meters above the surrounding terrain, nearly as tall as the Rocky Mountains, on a world that shouldn't have them. Here is why that matters. Mountains require a mechanism to push material upward against the force of gravity. On Earth, mountains are built by plate tectonics, the slow collision and subduction of crustal plates, driven by heat from the planet's interior. On Mars, the largest mountains in the solar system are ancient volcanic structures built up over billions of years by a mantle that was once active and is now mostly still. On Io, tidal heating drives volcanic construction. There is always a heat source. Something has to be doing the pushing. Pluto is small. Too small, scientists had assumed, to have retained enough internal heat from its formation to be geologically active. At its great distance from the Sun, there's no significant tidal heating. The expectation was a dead world, one that had cooled completely long ago, its surface shaped only by ancient impacts and slow chemical changes from cosmic radiation. The mountains said otherwise. They are not ancient. Geologically, they appear young, hundreds of millions of years old at most, possibly much younger, because they show no impact craters on their surfaces. In the outer solar system, a surface that lacks impact craters is a surface that has been renewed recently, because impacts accumulate over time, and old surfaces are covered in them. The mountains of Pluto are fresh. Something is or was recently, moving material around, building structure, reshaping the surface. The heat source for this activity is not yet fully understood. Pluto may have retained more internal heat than models predicted. There may be radioactive decay happening in its interior on a timescale that keeps a small amount of heat flowing outward. There may be processes in Pluto's interior that the models hadn't accounted for. Whatever the answer, Pluto is not the dead, inert ball of frozen rock and ice that decades of assumption had made it. And then there was the heart. Tombaugh Regio turned out to be a nitrogen glacier. The bright white plain is made of nitrogen ice, and it is active. It flows, slowly, like a glacier of nitrogen driven by Pluto's cold internal dynamics. The surface is smooth because the flowing nitrogen continuously resurfaces it, filling in any craters that form. The region is divided. The left lobe of the heart, called Sputnik Planitia, is the glacier itself. It sits in a large basin, roughly the same size as the impact basin that likely formed it billions of years ago, and the nitrogen has pooled there over geological time, accumulating into a sea of frozen gas perhaps kilometers deep. The nitrogen flows. Convection cells in the nitrogen ice, warmer material rising, cooling, sinking, create a pattern of irregular polygons on the surface visible in the images, each polygon perhaps tens of kilometers across. Pluto is cold enough that nitrogen freezes solid, but even solid nitrogen under the right conditions of temperature and pressure can flow. The glacier is in slow, continuous motion. On the edges of the nitrogen glacier, where it meets the water-ice highlands around it, the nitrogen ice appears to have carved channels in the water ice, like a frozen river delta. Pluto has glacial geography. It has features that, if you showed them to someone without context, they might describe as landscape. The atmosphere of Pluto, when New Horizons analyzed it, proved to be thin, but layered and structured. Haze layers, created by photochemical reactions in the upper atmosphere, hung above the surface in multiple distinct bands. When the spacecraft looked back at Pluto after the closest approach, it captured an image of Pluto backlit by the distant sun, a thin blue ring of atmosphere glowing around the edge of the dark disk. Pluto has a blue sky, not from the same mechanism that makes Earth's sky blue, the scattering of sunlight by nitrogen molecules, which affects blue wavelengths more than red. On Pluto, the blue comes from haze particles, small organic molecules created when sunlight breaks apart nitrogen and methane molecules in the upper atmosphere, and they recombine into larger, heavier compounds called tholins. These tholins rain down onto the surface, coloring it red. The dark red patches on Pluto's surface are organic chemistry, the same kinds of complex carbon compounds that were building blocks for life on early Earth, accumulating on a frozen world in the outer solar system over billions of years. The possibility of a subsurface liquid water ocean on Pluto was proposed after the flyby, based on several lines of evidence. The large impact basin that became Tombaugh Regio would have left a dense impactor residue at the point of impact, creating a mass concentration. If there were no liquid layer to allow the basin to reorient over time toward Pluto's tidal axis, it would be offset from where it actually is. Its position suggests that reorientation happened, which requires a liquid or mobile layer beneath the ice. Models of Pluto's interior, incorporating what New Horizons measured about the surface and gravity field, suggest that liquid water may persist deep beneath Pluto's surface, kept from freezing by a small amount of antifreeze chemistry and residual internal heat. Pluto may have a liquid water ocean beneath its frozen surface. In the outer solar system, at the very edge of the Kuiper Belt, in a world that receives barely any sunlight, a world that had been dismissed as a minor, probably boring dwarf planet. There may be liquid water. Every ocean we find in the outer solar system, Europa, Enceladus, Ganymede, Titan, and now possibly Pluto, is another answer to the question that underlies all astrobiology. Where can life exist? And the answer that the outer solar system keeps giving us is further out than we thought, at colder temperatures than we thought, in places that look inhospitable from the outside. Charon, Pluto's largest moon, deserves its own moment, because what New Horizons found there was nearly as surprising as what it found on Pluto itself. Charon is half the diameter of Pluto. In terms of the ratio of companion to primary, this is the largest moon-to-planet or moon-to-dwarf planet ratio in the solar system. The two bodies are tidally locked to each other, always showing the same face to each other, orbiting a common center of gravity that sits in the space between them rather than inside either body. If you stood on Pluto's Charon-facing hemisphere, Charon would hang fixed in the sky, never rising, never setting. Enormous, 14 times the apparent diameter of the full moon as seen from Earth. A permanent feature of the sky. Charon's surface is darker than Pluto's, predominantly grey-blue water ice, rather than the brighter nitrogen ice of Pluto's plains. And across its surface runs a system of chasms and canyons that dwarfs anything on Earth. A canyon system near Charon's equator is roughly 1,600 kilometers long and in places nearly 9 kilometers deep, longer than the Grand Canyon by a factor of 10, deeper by a factor of 5. It appears to be a tectonic feature, a fracture system in Charon's crust, suggesting that Charon too underwent geological activity at some point in its past. Its interior expanding as water froze and cracked the overlying crust. At Charon's North Pole, there is a distinctive reddish-brown patch. Unlike the rest of Charon's grey-blue surface, the North Pole is clearly colored by the same kind of organic tholins that tint Pluto's surface red. But Charon shouldn't be producing its own tholins in significant quantities. It doesn't have the same atmospheric chemistry as Pluto. What appears to be happening is this. Pluto's thin nitrogen and methane atmosphere is slowly escaping into space, lost gradually because Pluto's gravity is not strong enough to hold it permanently. Some of that escaping atmosphere crosses the space between Pluto and Charon and is captured at Charon's poles, where it freezes in the extreme cold of Charon's polar winter. As the methane and nitrogen are exposed to ultraviolet radiation from the sun, they are transformed into tholins, coloring the pole. Charon's red North Pole is made of material that used to be on Pluto, chemically transformed and deposited by the slow leak of Pluto's sky. The two worlds are connected by more than gravity. They share chemistry, share history, and in a small, slow, ongoing way, Pluto is literally building Charon's polar caps out of its own atmosphere. Koth, the most pristine object ever visited. After Pluto, New Horizons was given a second target. The spacecraft still had fuel. Its instruments still worked. Its trajectory after the Pluto flyby would carry it deeper into the Kuiper Belt. A search was mounted using the Hubble Space Telescope for a Kuiper Belt object, a smaller, more primitive body than Pluto, that New Horizons could reach without changing its course dramatically. Several candidates were found. One was selected. Its official designation was 2014 MU69. The science team gave it a nickname, Ultima Thule, later officially renamed Arakoth, a word from the Powhatan language meaning sky. New Horizons reached Arrokoth on January 1st, 2019. And what it found was something that had never been seen before. Arrokoth is a contact binary. Two lobes, two separate objects, joined together at a narrow neck. The larger lobe was named Wenu. The smaller lobe was named Weo. Together, the combined body is roughly 36 kilometers in length. Small enough that if you placed it over a city, it wouldn't reach from one side to the other. But its shape tells a story. The two lobes are not random. They match in composition, in surface color, in surface texture. They are not two different objects that happen to collide at random. They are two objects that formed together from the same cloud of material in the early solar system, orbiting their common center of gravity at a very slow speed, gradually spiraling toward each other over millions of years as tidal interactions and radiation pressure slowly changed their orbits, until finally, very gently, they touched. The contact between the two lobes shows no evidence of a violent collision, no compression features, no fracturing, no evidence of significant impact force. Wenu and Weo came together slowly, at extremely low speeds, and simply settled against each other. This is called pebble accretion, the process by which small solar system bodies are thought to have formed. Not by violent collision, but by the gradual accumulation of smaller particles drawn together by self-gravity and electrostatic forces in the protoplanetary disk that surrounded the young sun. The larger planets formed by a similar process eventually, but the bodies that assembled them were destroyed, processed, melted, mixed, and transformed over billions of years. There is no pristine record of that early assembly process visible in the planets themselves. Arrokoth is different. Arrokoth formed in the Kuiper Belt, far from the sun, in a region cold enough and sparse enough that it has been undisturbed for most of the solar system's history. No significant heating, no collisions violent enough to restructure it, no geological activity. The surface of Arrokoth has been sitting essentially unchanged for 4.5 billion years, since the solar system was new. When New Horizons photographed Arrokoth, it was photographing the solar system's childhood in as close to its original form as anything we have ever or will ever see. The smooth red lobes, coated in tholins from billions of years of cosmic radiation processing the surface organics, are a direct record of the conditions in the outer protoplanetary disk before the planets finished forming. The shape confirmed something important. The current leading model of planet formation, that larger bodies assembled from smaller objects that came together gently, not through catastrophic high-speed impacts, was already favored, but Arrokoth provided something models rarely provide: a direct, preserved physical record of the process itself. The two lobes are the process, frozen in place, still touching after 4.5 billion years of cold quiet. That is what New Horizons found at the edge of the known solar system. Not just a dwarf planet with unexpected mountains and glaciers and blue skies. Not just a binary moon pair exchanging atmosphere, but a genuine relic of the moment of creation, preserved in the cold dark beyond Neptune, waiting for something to come and look at it. What New Horizons is doing now? New Horizons is currently approximately 68 U from the Sun, well beyond Pluto's average orbital distance of about 39 ATU. Its instruments are still active, still measuring the space around it. It has not yet reached the termination shock, the inner boundary of the heliosheath where the solar wind first begins to slow. The Voyagers crossed the termination shock at roughly 84 to 94 AU. New Horizons will reach that region in the 2020s, to 2030s. But New Horizons carries something the Voyagers didn't. Modern instruments designed specifically to measure the interstellar medium and the structure of the heliosphere. The Voyagers were not designed with crossing the heliopause in mind. That possibility was not foreseen when they were built. Their instruments for measuring plasma, magnetic fields, and energetic particles were designed for the planetary encounters, and many of them were still useful at the heliopause. But their measurements have gaps. New Horizons has instruments designed from the start to characterize the outer heliosphere and, eventually, interstellar space. Its SWAP instrument measures the solar wind and its interaction with the outer heliosphere. Its PEPAS-SI instrument detects energetic particles from outside the heliosphere. As New Horizons moves outward, it is making measurements that will allow scientists to build a more complete picture of the heliosphere's structure than the Voyager data alone can provide. 2 crossing points: Voyager 1 in the north, Voyager 2 in the south, can only tell us about 2 regions of the heliosphere. New Horizons is heading in a different direction still, in the plane of the solar system, adding a 3rd line of measurement through this vast structure. The heliosphere, it turns out, is not uniform. It varies with direction. Understanding why requires measurements from multiple directions, which our 5 spacecraft between them are providing. New Horizons is also mapping the distribution of hydrogen gas in the outer solar system and the Kuiper Belt, measuring how the solar wind carries hydrogen far beyond the planets. This hydrogen distribution matters for understanding the local interstellar medium, the gas and dust that surrounds the solar system, and for understanding how the sun's influence shapes the space around it over thousands of AU in every direction. The mission currently has power to operate until at least the early 2040s. By then, New Horizons will be past 100 ATU from the sun, approaching the termination shock and beginning to sample the helio sheath, the same turbulent mixing zone the Voyagers traversed before their final crossing into interstellar space. We have not heard the last from New Horizons. Voyager 1 in interstellar space, what it actually found. On August 25th, 2012, Voyager 1 crossed the heliopause and entered interstellar space. The date was determined not from the crossing itself. There is no obvious line, no marker visible to the naked eye, but from measurements. The instruments aboard Voyager 1 detected, on that date, a sudden sharp change in the density of the plasma surrounding the spacecraft. Plasma density dropped dramatically in the solar wind region, then abruptly increased as the spacecraft entered the interstellar medium. Simultaneously, the energetic particle environment changed. Solar energetic particles dropped sharply and galactic cosmic rays increased, confirming that the spacecraft had moved from a region dominated by the Sun to a region dominated by the broader galaxy. What Voyager 1 found in interstellar space was not empty space, not in the way the word empty usually implies. The interstellar medium, even far from any star, contains plasma, ionized gas, predominantly hydrogen, at densities that are essentially vacuum by any earthly standard, but measurably present. The density is perhaps 1 particle per cubic centimeter, orders of magnitude thinner than the best laboratory vacuum achievable on Earth, but not zero, not nothing. The magnetic field orientation changed significantly at the heliopause. Inside the heliosphere, the magnetic field is structured by the solar wind, spiraling outward from the Sun in a pattern first described by physicist Eugene Parker in 1958. Outside the heliosphere, the magnetic field is interstellar. shaped by the galaxy, not the sun. The direction of the field lines changes at the boundary. One of the most interesting findings from Voyager 1 in interstellar space involves plasma waves, oscillations in the plasma that propagate at specific frequencies depending on the plasma's density. By listening for these oscillations with Voyager 1's plasma wave instrument, scientists can measure the density of the interstellar plasma with high precision. And what those measurements have shown is that the interstellar medium in the solar neighborhood is not uniform. There are regions of different density which the spacecraft has passed through over the years since its crossing. The interstellar medium is structured, varying on scales of tens of AU, in ways that the measurements are just beginning to characterize. Voyager 1 has also confirmed that the heliosphere provides genuine shielding against galactic cosmic rays. Inside the heliosphere, the solar wind pushes back against the flow of cosmic rays from the galaxy, reducing their flux. The increase in cosmic ray intensity after Voyager 1 crossed the heliopause directly confirmed this shielding function. Life on Earth benefits from the heliosphere's protection in the same way it benefits from Earth's magnetosphere. It sits inside a nested set of protective bubbles, the innermost being the magnetosphere, the outermost being the heliosphere itself. Understanding the heliosphere is therefore not just an abstract scientific question. It is relevant to understanding the conditions that allowed life to develop on Earth, and to evaluating whether other planetary systems with similar stellar winds might provide similar shielding for any life that develops around other stars. Voyager 2 in interstellar space. The second crossing, Voyager 2, crossed the heliopause in November 2018, 6 years after Voyager 1. It crossed at a different point, lower in the solar system, tilted below the plane of the ecliptic, and its crossing provided something that a single data point cannot: a comparison. If the heliosphere were perfectly symmetrical, the two crossings would have been at the same distance from the Sun and would have shown the same features. They did not. Voyager 2 crossed the heliopause at roughly 119 AU from the Sun. Voyager 1 had crossed at roughly 122 AU. A small difference, but real, and in a consistent direction. The heliosphere, in the direction Voyager 2 traveled, is slightly smaller. This asymmetry is consistent with the Sun's motion through the interstellar medium. As the Sun moves, the interstellar medium presses harder on the leading side, compressing the heliosphere there. And the heliosphere extends further on the trailing side. More significantly, Voyager 2 crossed the heliopause with its plasma instrument still functional. Voyager 1's plasma instrument had failed decades earlier, before the heliopause crossing, so its measurements of the plasma environment at the boundary were incomplete. Voyager 2 carried a working plasma instrument across the boundary, providing direct measurements of the plasma density and temperature on both sides of the heliopause. What those measurements showed was a narrow boundary. The heliopause is not a gradual transition. It is a relatively sharp surface. The solar wind plasma drops. The interstellar plasma rises within a region only a few AU thick. The two plasmas remain largely separate, despite the turbulent helio sheath on the inside. The boundary holds. The magnetic field also changes at the Voyager 2 crossing. But interestingly, the total strength of the magnetic field remains similar on both sides of the heliopause. The solar magnetic field and the local interstellar magnetic field happen to have roughly similar strengths in this region. They differ in direction, however. The interstellar field lines are oriented differently from the solar field lines, and the transition between them happens at the boundary. One of the surprises of the Voyager 2 data was the detection of a thin, hot layer just inside the heliopause. The solar wind, decelerated and heated in the heliosheath, forms a thin, hot layer in the outermost part of the heliosphere that pre-crossing models hadn't clearly predicted at the observed temperature. The actual boundary region is more complex than the simplified models suggested, with structures and layers that the models are now being updated to accommodate. This is the scientific value of having two crossing points. Not just confirming the first with the second, but revealing that the first was not representative of the whole. The heliosphere is not symmetric. Its shape, its internal structure, its boundary dynamics, all of these vary with direction, and understanding that variation requires measurements from multiple directions. Our 5 spacecraft are providing those measurements slowly, over decades, as they move outward into the dark. The coming silence, Voyager 1's power comes from 3 radioisotope thermoelectric generators, RTGs, that convert the heat from the radioactive decay of plutonium-238 into electricity. Each RTG produces less power than the one before it, as the plutonium decays. When the spacecraft launched in 1977, the RTGs produced roughly 470 watts. By 2026, that figure is closer to 250 watts, and it continues to drop by about 4 watts per year. The spacecraft needs a minimum power supply to operate its instruments and communication systems. As power drops, instruments have to be turned off, one by one, to preserve enough power for the radio transmitter and the essential navigation and attitude control systems. Several instruments were already powered down in the early 2000s to extend the mission. Current projections suggest that Voyager 1 will be able to maintain communication with Earth until approximately 2025 to 2030. Some estimates push to the mid-2030s, depending on how aggressively instruments are managed. By then, the power will simply be too low to operate the transmitter at a level detectable from Earth. And then it will be quiet. There will be no event, no final transmission announcing the silence. One day, the Deep Space Network dishes will listen, and there will be nothing. The carrier signal that has been there, faint but consistent, for nearly 50 years, will stop. Voyager 2 has a slightly different power trajectory and may go silent around the same time, given that both spacecraft launched in the same year with essentially identical power systems. After the silence, the spacecraft continue. They don't stop when they stop transmitting. They will move outward at their current speeds for billions of years, slowed only slightly by the sun's gravity and by the extremely thin gas and dust of the interstellar medium. In roughly 40,000 years, Voyager 1 will make its closest approach to a star, Gliese 445, in the constellation Camelopardalis, passing within about 1.7 light-years. In 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in our night sky. In 40,000 years, Gliese 445 will simply pass. Voyager 1 won't enter its system. It will continue, slightly curved perhaps by the gravitational interaction, but essentially undisturbed, into the deeper galaxy. The golden records on each Voyager will outlast everything. The copper discs, plated in gold, protected from radiation damage by the spacecraft surrounding them, should survive for far longer than the spacecraft's operational lifetime, far longer than the civilization that sent them. Their estimated survival time is on the order of 1 billion years, not before some degradation occurs, but before the information becomes unrecoverable. In 1 billion years, the sun will have brightened. The Earth may no longer be habitable. Human civilization, whatever it is or was, will be separated from the present by a gulf of time larger than the current age of complex life on Earth. The Voyagers will be out there still. What all five collectively taught us. It is worth stepping back from the individual stories to ask what these five spacecraft, taken together, changed about our understanding of where we live. Before the Pioneers and Voyagers flew, the solar system was largely inferred. We knew the planets from telescopic observation, their sizes, their orbits, their colors. We knew some of their moons. We knew the rough shape of the asteroid belt and had theoretical ideas about what lay beyond Neptune. But the physical reality of the outer solar system was speculation, model, inference. Nobody had been there. These five spacecraft went there, physically, and what they found consistently surprised the people who built the models. Io was supposed to be dead. It has more active volcanoes per square kilometer than any body in the solar system. Europa was supposed to be a cold, cratered ball of ice. It has a liquid water ocean larger than all of Earth's combined. Titan was supposed to be a minor moon. It has a nitrogen atmosphere thicker than Earth's, and a chemistry that resembles the chemistry of early Earth. Pluto was supposed to be a dead, uniform ball of frozen rock. It has active glaciers, young mountains, a blue sky, and possibly a subsurface ocean. The outer solar system is not a cold, dead periphery. It is a biologically significant place in the sense that it contains the conditions: liquid water, energy sources, complex chemistry that we associate with the possibility of life. Every mission to the outer solar system has found more of these conditions than was expected. This is not coincidence. It is telling us something about the universe that we needed to hear. Life, if it exists beyond Earth, is probably not in the inner solar system, baked by sunlight and scoured by radiation. It is probably in the outer solar system, in the dark, under ice, in subsurface oceans kept liquid by tidal heating or residual internal heat, doing chemistry in the cold quiet of a world that looks, from the outside, like it has nothing going on. The five spacecraft also taught us the structure of our own protective bubble. The heliosphere, whose existence was theorized before any spacecraft visited it, turns out to be complex, asymmetric, variable, and real in ways that models didn't fully predict. It shields the inner solar system and everything in it from the full flux of galactic cosmic rays. Without it, Earth's radiation environment would be meaningfully different, and the development of life might have followed a different path. Understanding the heliosphere, its shape, its dynamics, its interaction with the interstellar medium, is directly relevant to understanding why life was possible here. And the only way to understand it was to go through it, which is what our five spacecraft did. The question of the messages. There are two golden records traveling through interstellar space right now. One on Voyager 1, one on Voyager 2. There are two golden plaques on Pioneer 10 and Pioneer 11. Four physical objects carrying curated fragments of humanity moving outward from the sun at tens of thousands of kilometers per hour. In 1 billion years, they might still exist. The question is whether anything will ever find them. The honest answer is, almost certainly not. The galaxy is, on most scales that matter, empty. The distance between star systems averages several light years. A spacecraft moving at 35,000 miles per hour, roughly 50,000 kilometers per hour, covers about 1.5 HURU per year. One light year is about 63,000 AUM. Reaching the nearest star would take roughly 75,000 years at Voyager's speed, assuming you were headed there, which the Voyagers are not. They are headed in whatever direction their trajectories took them, not toward any particular star. The probability of these spacecraft moving through the empty space between stars, happening to encounter another civilization's detection range over the span of 1 billion years, is genuinely small. Astronomers have done the math. The estimate is that there is roughly a 1 in 10 billion chance that the Pioneer plaque will be found within the next 10 billion years by an extraterrestrial civilization. Not zero, but very close to zero. Carl Sagan knew this when he advocated for the golden record. He knew the odds. He understood mathematically that the chance of the record ever being played was negligible. He included it anyway. This is worth sitting with, because it tells us something about why we did this that goes beyond the practical. The golden record is not a strategy. It is not a communication plan. It is a gesture, a reaching out in the full knowledge that the reach will almost certainly come to nothing. There is something deeply human about that. We make gestures of connection knowing they might not land. We send letters to addresses that may no longer exist. We plant trees whose shade we will never sit in. We write things knowing that the people we most want to read them may never see them. We reach out across distances that may swallow the gesture entirely, because something in us insists that the reaching matters regardless. The golden record is that impulse at its most extreme. Sent on a spacecraft that will travel for billions of years through empty space, almost certainly never encountering anyone. Carrying music and greetings, and a woman's brainwaves, and the sound of rain. Because we had the chance to send something. Because we had the capability. Because it would have felt wrong, deeply wrong, in a way that's hard to articulate but easy to feel, to launch something into the permanent interstellar dark and not say anything. You don't throw a bottle into the ocean without a message. You just don't. And so there is a record out there, 2 of them, carrying our music and our voices, and the sound of waves on a shore that is now 165 AU away, carrying the sound of a kiss. Carrying Chuck Berry and Johann Sebastian Bach, and Blind Willie Johnson playing slide guitar in 1927 in a way that made the universe sound like it had weight to it. Traveling through a galaxy that does not know it exists. Moving past stars that will never shine warmth on it. Heading somewhere it will never arrive. And it is one of the most extraordinary things we have ever done. What the 5 spacecraft are, really. Let me try to say what these 5 spacecraft actually are. Not what they are technically or scientifically, but what they are in the deeper sense. They are proof that we were here. Not in the geological sense. The Earth itself is proof that life was here. Our fossils will be readable in the rock record for hundreds of millions of years. Our civilization's electromagnetic signals have been leaking into space for over a century. A bubble of radio and television and radar, expanding outward at the speed of light in all directions. But those are accidental evidences. Byproducts of existing, not intentional statements. The 5 spacecraft are intentional. Someone decided to send them. Someone decided to put the plaque on Pioneer 10. Someone decided to record music and greetings and the sound of rain and put it on a golden disc and launch it into the dark. Someone sat down and thought, if something out there ever finds this, what do we want them to know about us? And those choices, what to include, what to leave out, what we thought mattered enough to carry into eternity, are themselves a portrait, not of human biology or human technology, but of human values. Of what we reached for when we reached. We reached for bark. We reached for the sound of a kiss. We reached for a mathematical diagram and a pulsar map and the brain waves of a woman thinking about love and the history of the world. We reached for the things that made us, in the honest assessment of the people who assembled the record, most fully human. That is the portrait we sent. That is who we said we were. And it is out there now, moving through the dark between stars, past the last measurements that our instruments can make, past the heliopause, past the termination shock, into the space that belongs to the galaxy rather than the sun, moving through a universe that has been here for 13.8 billion years, that will be here for trillions more. That contains 2 trillion galaxies and more stars than there are grains of sand on every beach on Earth. 5 small metal objects carrying our fingerprints into all of that. Coming home, let's come back now. All the way back through 165 AU of space to this solar system. Back through the asteroid belt and past the rocky planets. Back to this small, blue, improbable world, orbiting an ordinary star in a quiet arm of a spiral galaxy that contains 100 billion other stars. Back to wherever you are right now. Whatever room, whatever bed or couch or corner of this planet, you are on Earth, right now, tonight. And out there, tonight, Voyager 1 is approximately 165 AU from where you're sitting. Its signal, traveling toward Earth at the speed of light, takes more than 22 hours to arrive. Engineers at the Deep Space Network, somewhere in California, or Spain, or Australia, are pointing dishes at a patch of sky and listening for a whisper from hardware launched before most of them were born. Voyager 2 is at 135 AU9, also transmitting, also still making measurements of the interstellar medium it is passing through, still sending back data about a region of space no human instrument had ever measured before these missions began. Pioneer 10 is at about 135 ATU, silent, carrying its golden plaque toward a star it won't approach for 2 million years. Pioneer 11 is at about 105 ATU, also silent, heading in the other direction, also carrying its message. And New Horizons is at about 60 AU, approaching the boundary of the heliosphere. Instruments active, data flowing back, the youngest of the 5, and the furthest from the edge, but moving there. All 5, right now, are out there, moving, going. They are the only human-made objects that will outlast everything else we have made. Every building, every bridge, every book, every archive will eventually end, burned, buried, eroded, decayed. The digital records we keep so carefully require power and maintenance and civilization to remain readable. The Voyagers require nothing. They simply move. They will be moving when the sun brightens and the oceans begin to dry, and whatever remains of humanity faces the consequences of living on a planet with a middle-aged star. They will be moving when the Andromeda Galaxy begins its slow collision with the Milky Way, 4.5 billion years from now. They will be moving when the merged galaxy settles into its final elliptical shape, billions of years after that. There is something almost unbearably strange about this fact, that we made things that will outlast us by such an enormous margin, that the most durable artifacts of our civilization are not our great buildings or our great libraries, but 5 spacecraft, each smaller than a school bus, made of aluminum and plutonium and copper wire, moving through the dark at 35,000 miles per hour. There is one last thing worth sitting with before we close tonight. When Voyager 1 turned its cameras around in 1990 and took the pale blue dot photograph, the image of Earth as a single pixel of light in a vast, dark frame. Carl Sagan wrote something about it that has stayed with people in the decades since. He pointed out that everything that has ever mattered in human history happened on that dot. Every act of kindness, every war, every piece of music ever composed, every painting, every prayer sent toward a sky that, from the other side of the solar system, doesn't look like anything special. Every person who ever lived, every dream and grief and triumph and failure, all of it on that one pale pixel. This is the perspective that 5 spacecraft brought us. Not cheaply. Decades of scientific labor, careers spent tracking signals across billions of miles, engineering of extraordinary precision and care. But they bought it. The view from outside. The view that shows us what we actually are in terms of scale. And the remarkable thing, the thing that is easy to miss if you're not careful, is that this view doesn't make us small in the way that matters. Because small and insignificant are not the same thing. Those 5 spacecraft are small. They are extraordinarily, almost embarrassingly small relative to the distances they travel. A spacecraft smaller than a car, moving at 35,000 miles per hour, through a solar system 200,000 AU across, toward a galaxy 100,000 light-years in diameter. In terms of physical scale, the spacecraft barely register. But they are there, and we sent them. And on 2 of them we put music. We put the sound of our world. We put the mathematical constants that describe the physics of our universe as a kind of handshake to whoever finds them. We put a raised hand on a small gold plaque and flung it into the dark and said, "This is what we looked like. This is what we heard. This is what moved us enough to carry it with us into forever." The universe does not care about this gesture. The stars around which Voyager 1 will pass in 40,000 years do not know a spacecraft is coming. The galaxy does not register our presence. On the scale of physical reality, we are noise too faint to detect. But we are also the only thing we know of that looks at the night sky and wonders. That builds instruments to measure what is there. That works out the physics of how it all behaves. That feels something when it understands. We are very small, and we reach very far, and those 2 things together are the most human combination imaginable. Tonight, wherever you are on this planet, you might be able to see the sky. Depending on your weather, your city, your hour, there might be stars. There might be a moon. There might be nothing but clouds and the glow of streetlights. Either way, up there, somewhere in the general direction of the constellation Ophiuchus, is Voyager 1. You can't see it. It's far too small and far too dim. But it's there, moving outward at 17 kilometers per second, away from the sun, away from Earth, away from everything familiar, into the space between stars. And on it, a gold-plated copper disc holds music that was recorded on Earth decades ago. Waves breaking on shore, a mother and child, blind Willie Johnson playing guitar in a way that makes the universe feel lonelier and warmer at the same time. Those sounds are out there. They are real. They are in the dark between the stars right now, tonight, while you sleep. Let that be the last thought before sleep. Not the terror of the scale, though the scale is real. Not the loneliness, though the dark is genuine, but the reaching itself. The extraordinary, stubborn, beautiful reaching of a species that looked at the darkness and sent music into it anyway. That is who we are. That is what we did. Good night.